So we're entering the second part of the class right now, and this part of the class is entitled F-tests and one-way ANOVA. And it, we're moving toward testing hypotheses that we haven't seen before. So we are expanding the set of hypotheses from maybe just making a comparison between a sample and a mean or two different means to other things that may be of practical interest from a statistics perspective. And the first thing that we're going to examine is variance. Variance is a measure of the dispersion of different data points from the mean. And variance has practical importance in that we may be very interested in how often, I guess to say it is, we get outcomes that are far away from the mean in either direction. So maybe if you think about the number of tips that you earn in an evening as a waiter or a waitress or a bartender, something like that, that may vary quite a bit. And you know that it varies by night, but it also varies by restaurant. And so you may think of working at a restaurant like Applebee's where you have a number of families come in and they're going to tip pretty standard percentages. And you may be comparing that to a place like Plates on the Square where, if you're working as a bartender on the second floor, you may get really good tips or really bad tips. The means may be kind of similar, Applebee's and Plates on the Square, but in Plates you may have more really good nights or really bad nights. And so that's something that we want to examine more thoroughly, and we're going to do that with what's called an F-test. And so the premise behind the F-test is that we take two samples, both from normal populations. It could even be the same normal population, and the populations have the same variance. We compute some sample variances and divide the two variances. So we have two samples from populations, and we compute two sample variances. Each sample has its own sample size. Now this sample could be the same, it could be different. Those ratios have their own distribution. So what the ratio is I am just dividing a large variance by a small variance and spitting out a ratio. And we're seeing how many times larger the large variance is than the small variance. Those ratios differ depending on the sample size. So you're more likely to get large variances with small samples because if you think about calculating a variance, it's 1 over n minus 1. Well, n is small. Okay? And those ratios have their own distribution. It's called an F distribution. Each combination of sample size has its own distribution. So we will have a large number of critical values when we look at an F table. F distribution has no negative values because variances are always positive, but you should be unlikely to get really high F stats by chance because the premise is that the population has the same variance. And then we're testing to see whether or not our two samples have the same variance. So the null with the F stat is that the variance of group 1 is equal to the variance of group 2. The alternative is that they're not equal. The F stat, you see that right here, F for F stat. I put the large variance on top, we'll just call it group 1, and the small variance on the bottom, that's group 2. To circle back as to why we have interest in doing this, I pointed out an example of being interested in the variance of tips. How likely is it that, we have a situation where it's just bad nights, good nights versus like a more steady stream of tips throughout. That's going to influence how you choose to spend. But you can also think of it in the guise of investing. So consider investing in two companies in the same sector. Maybe it's the energy sector. So you're looking at like Southern Company versus Duke Energy or something like that. They could have similar mean returns because they have similar product demand, but if they have completely different variances, you may have to look at that when you invest in your portfolio. So if one is really risky compared to the other, you may want to avoid it or you may not. It depends on how much risk you want to take on, but it might be something nice to know. And so the F-stat has some usefulness in those dimensions. Okay, so I want to think just a little bit more about samples. They could have the same sample size or be different. That's going to influence the variance. So small samples may yield imprecise estimates of the variance because you only have a few observations. So they're going to yield larger variances. Think of getting one data point far away from the mean compared to multiple data points far away. It will impact the ratios you expect to see. So if I am comparing samples of 2 and 5, I might think that comparison involves a higher critical value than samples of 20 and 45. We account for this explicitly in the F table. We have two sets of degrees of freedom, one for the sample size of the large variance, one for the sample size of the small variance. When we make the F table, we put the largest variance on top and the smallest one on the bottom. Large variance goes on top, small variance on the bottom. Degrees of freedom for the numerator, that's with the large variance. Number of observations for that sample minus 1. Degrees of freedom for the denominator, it should say denominator there. Number of observations minus 1. So I look at the sample size for the large variance, that goes in the numerator. I subtract 1, I go to that column. I look at the sample size for the small variance, that goes in the denominator. I subtract 1. Those are the rows of the F table. So having a sample size where the large variance is 4 and the small variance is 5 is different than having a sample size where the large variance is 5 and the small variance is 4. We look at those differently. They're close, but they're not the same. We force the F-stat to be bigger than 1. So when we do a two-sided hypothesis test, because we don't randomly put a variance on top and bottom, we always make it greater than 1, we are looking at one-sided values, and so it kind of boils down to the T-table where the 95% one-sided is the same as the 90% two-sided. It's just with the F-table, you're only looking in one column. The column is just a huge page of numbers. So, long story short, for this class, we're going to do 90% confidence tests for the F table and use 95% one-sided values to test it. Okay, this is just an example of some F distributions that may be of interest. Okay, so here is an example of an F test for variance, and this should actually read not equal. So I'm going to fix that real quick so we don't get confused there. Let's change it on the slides. Let's go back to the slides really quick. The null is that the two variances are equal to each other. The alternative is that they're not. I'm going to recompile it and reopen it. So I don't want to have some confusion and make a mistake here. Okay, now let's reopen the file. Okay, sorry about that. The null is that group 1 is equal to group 2. Group 1 going through town. So you're driving past Enterprise Rent-A-Car, you're driving past Lake Carroll, Martin's Biscuit, old Kmart building, you're driving through downtown, then you're going over on 60 or 27 over to Maple Street to get to campus. That's one way to get to campus. The other way is to go around on the bypass. You drive past Noonan Road, you drive past 27 on the south side, you see the Target, you drive past Hayes Mill, you come in that way. The mean times are 9.5 and 10.2, but the variances are 43.2 and 34.9. So we have a larger variance going on the bypass than going through town. But we also sample 15 times going through town, 9 times going on the bypass. So the variance going through town, 43.2. Okay. Going on the bypass, 34.9. We sample more times going through town, 15, 9 through the bypass. All right, and we are just going to do a two-sided hypothesis. It should say two-sided hypothesis, and we'll fix the more dispersion. It should say that there is a difference going through town than on their bypass. So I'll fix that for the slides. All right, so we're doing a two-sided hypothesis test. The null is that they're equal. The alternative is that they're not. The F-stat is super easy. I just take the variance of the large one, which is 43.2, and I divide by 34.9. That's 1.238. Critical values, I go to the F table, and this is the F table. And you can see at the top that it's 21 pages long. It's 21 pages of critical values. Lots of critical values with the F table. Okay, so take a look at the top of the F table. The second page, you see alpha equal to 0.10. That's a one-sided p-value. So that is testing a hypothesis at the 90% level. With a one-sided hypothesis, we want to do a two-sided hypothesis at the 90% level, so we have to skip all the 80% and go to 90%, as seen here, 90%. Okay, and the one-sided value is associated with 95. So because we force the F-stat to be bigger than 1, we only look to the right. We don't look to the left. And so we're only looking on one side of the ratio where they're equal. So it's similar to a one-sided hypothesis test in that way, but we're doing a two-sided hypothesis, so that's why you see this alpha equal to 0.05 here, but you see a two-sided confidence interval of 90%. Okay, take a look at the numerator. This is the sample size minus 1 for the large variance. Let's look at, those are the columns. So this is the numerator of the F-stat, and those are the columns. Let's look at the denominator. Those are the rows of the F table. The sample size minus 1 for the small variance. Okay. We sampled 15 times through town. Town was the larger variance. In the F table, we would go to column 14. No column 14 here on this page of the F table. No column 14 here on this page of the F table. There is a column 14 here on the third page of our F table for a two-sided hypothesis of 90%. So I'm at column 14. I go to row 8. Why? Because I went 9 times around the bypass, so that's 9 minus 1, which is 8. Column 14, row 8. Column 14, row 8, 3.24. My F-stat is 1.238. It is smaller than 3.24. Based on these samples, I can't rule out that there's the same variance for going around town compared to going through town. So the F-stat is pretty easy to do. You just put the large variance on top, look at the sample size of the large variance, subtract 1, that's your column. Small variance goes on the bottom, look at the sample size of the small variance, subtract 1, that's your rows of the F table. There are 4 pages for each confidence level. For this class, we're only going to do 90%. Now, Excel will do this for you. You can do an F-test, and it will compute a p-value for you. And it will do a little bit more with the data analysis F-test, and you can see that right here. To summarize the F-test, we only do two-sided hypotheses. We don't do one-sided hypotheses in this class. We only use 90% confidence level, 95% one-sided, alpha equal 0.05 in your F table. We don't do any other levels, although we could. I mean, so you see the F table, you'll see it when we put it on course 10. There are 20 pages. We could pick any confidence level that we want, but we're only going to use 90% in this class.